Hello everyone, my name is Sidhartha and I'm a software engineer at MinIO. Here at MinIO, we build object storage and we also spend some resources contributing back to the community. One of the things we've been working on is COSI, which is what I'll be introducing today. COSI stands for Container Object Storage Interface. It is an interface similar to CSI or CNI, which are Container Storage Interface and Container Networking Interface, where CSI is for block devices, COSI is for object storage buckets. What COSI does is it acts as a bridge or an interface between your containers in the Kubernetes world, which would be running as pods, and object storage systems. So the name Container Object Storage Interface. What COSI does is it abstracts different implementations of object storage and provides a unified API so that any workload that wishes to use buckets can use that unified API to request buckets, and COSI would take care of translating those requests to particular object storage implementations. Finally, all of this is enabled just with three core primitives in COSI. One is bucket creation, one is bucket deletion, and one is bucket provisioning. There are a few things to notice here in this list. One is all operations are around buckets. What COSI does is it manages the life cycle of buckets itself, creation, management, deletion of it. It does not get into the data path. It does not get into the creation of objects, none of that. Second thing to note here, creation and deletion are easy to understand, they're straightforward. Provisioning though, bucket provisioning are the set of steps that are conducted by COSI after a bucket is created. The steps to create credentials for the bucket and then convert those credentials into a form that the pod can accept and use. So these are the three core primitives of COSI. Now, what I have here is the list of things that I wish to cover during today's presentation. To begin with, I want to explain the use cases that we wanted to solve using COSI and why they're important. Secondly, I will show you the API that COSI exposes as it is today. This API will be the primary mechanism of using buckets in Kubernetes moving forward. And finally, I'm going to explain the internals and the architecture of COSI, which will directly lead to how vendors can integrate with COSI and provide their object storage service natively on Kubernetes. So let's get started with the use cases. So the first use case that I've mentioned here is kube nativity. If you notice in Kubernetes, pretty much every cloud provider specific resource or I would say infrastructure resource such as load balancers, nodes, block devices, just as few examples, are abstracted by Kubernetes. And you can drive the lifecycle of load balancers, the configuration of them, the lifecycle of block devices and its configuration as well, purely through a Kubernetes API. You never have to go talk to the vendor system, you never have to talk to the backend to figure out how to provision these things. However, such a system or such an API does not exist for object storage. COSI fills that need. So COSI aims to have a purely Kubernetes API for creating object storage buckets, managing them and utilizing them. Now, once you become a Kubernetes API, you get all the benefits that come with being a Kubernetes API. For instance, Kubernetes resources are naturally grouped into namespaces. And namespaces are so ubiquitous today that organizations that use Kubernetes use namespace as boundaries for teams that use Kubernetes. What I mean by that is, one team that is a part of the organization-wide cluster would manage one namespace, their namespace. Another team would manage their own namespace, and the two resources managed by each of them, the resources managed by each of them will not collide unless it is explicitly required that they somehow talk to each other. So namespace provides natural isolation for resources, and we wanted to provide the same for buckets too, because it is reasonable to expect that buckets used by one team need not be shared by buckets used by other team, and when needed we can enable that though. Finally, another aspect of kube nativity is the lifecycle of workloads. We wanted the ability for COSI to work with pods natively. And what I mean by that is, if there is a pod that requests a bucket, then when the pod starts up, it should be able to get a new set of credentials. And when it goes away, the credentials should be automatically cleaned up. And then if a pod is using credentials to access a bucket, those credentials shouldn't be deleted even by mistake. And also when you plug in natively into the lifecycle of workloads in Kubernetes, you get all the benefits of just the native integration. Without going into the details, I'll be able to answer it separately at the end of this talk, but without going into the details, these are the three specific core use cases of making COSI, of wanting to make COSI kube native. So this was the first goal, that is to bring a kube native API for consuming object storage. This is the most important one. The second use case is self-service. Kubernetes has enabled organizations to use resources, infrastructure resources, without always having to rely on an administrator. For instance, as it is today, CSI enables developers, without relying on an admin, to request for persistent volumes, block devices, and use them in their pods. There is no need for a centralized admin in this case to create a block device in the backend, which is how it was done traditionally, and provide it to the developer, who would then have to figure out how to work with that specific implementation of that system and use it. We wanted to create an API, or we wanted to create an experience where the developer is empowered, and the admin still has a role to play here. The admin's role is to define organization level policies, is to define access control roles, is to define quotas and limits of how much a bucket can be used or how many buckets can be used. So we wanted to create this dichotomy and form this boundary this way, where the developer is empowered more than they've ever been with respect to object storage, and the admin still has privileges that an admin would care about. Finally, this is a promise that Kubernetes itself makes as a general promise, that is, Kubernetes lets you be hybrid cloud or hybrid environment, really, where you can run some of your workloads on the cloud, some on prem, or have them be on two different clouds, say for disaster recovery reasons. So we wanted to do the same with object storage. We define two kinds of portability here. One is cross-cluster portability, one is cross-platform portability. Cross-cluster portability is where we wanted to have the ability to move a bucket, the COSI representation of a bucket, from one cluster, one Kubernetes cluster, to another. Now the two clusters may be in the same cloud environment, they could be in different cloud environments, but we wanted to enable that. Second is cross-platform portability. Cross-platform portability, what we mean by that is, we wanted to enable a workload to seamlessly switch between object storage providers, as long as the two object storage providers talk the same data API. If that one invariant is kept, then COSI can allow you to seamlessly switch, where your application will not have to change any configuration, won't even know that a different provider is providing buckets for you. Today S3 is a famous standard. Other than being a service, other than being a Amazon cloud product, S3 is also a protocol which services, which applications use regularly to exchange data with the S3 service. So all this portability is really meant for one important reason, which is to prevent vendor lock-in. So I'm going to take a small pause here and just to digest all this information that we've just discussed. We started off trying to understand what COSI is. COSI is a standard for utilizing object storage in Kubernetes, And then we talked about what are the core use cases we wanted to solve with COSI. Obviously, the first one is to enable Kube native object storage. Second is self-service, empower the developer. And third is portability, prevent vendor lock-in. Now we look at the API, which is the interface that COSI exposes and which is the primary mechanism by which you and I will interact with COSI. So let's start with this diagram again. I showed this diagram earlier. This shows an overall architecture of a Kubernetes cluster with COSI in it. What I'm trying to show here is the life cycle of a bucket. So a pod would request a bucket, workload would request a bucket, and COSI will understand that request and then talk to the object storage system and provision the bucket, provision credentials for that bucket, and bring it back and plug it back into your pod. So this is the very simple version of the lifecycle of a bucket. So there are two aspects here. One is the communication between the workload and COSI, which is the COSI API, and two is the communication between COSI and object storage. In this section, we'll focus on the communication between workload and COSI. So the workload would first need to specify that it wants a bucket. So we modeled that as a new Kubernetes resource type, a CRD, called bucket request. Bucket request literally is a declarative way to say I request a bucket. If you can see the bucket request I've shown on the screen here, it might not look like Kubernetes syntax, but semantically it expresses the same set of information that a Kubernetes resource would. I've just put it in this syntax so that it's easier to read. A bucket request, if you notice, there is a name, there's a namespace, and there's a bucket class. Now, the namespace, I've put it here deliberately to show that the bucket request is actually a namespace resource. The bucket request, since it is a namespace resource, let me take a step back and explain why it's important for it to be a namespace resource. The idea, the right way to manage Kubernetes clusters is to have developers or provide developers with free access within the namespace that they belong to, but keep cross namespace access exclusive to admins. So cluster level operations, cluster level Kubernetes resources should generally only be allowed to admins, and developers should generally be constrained to the namespace in which they work on. So in such a model, bucket request is a namespace resource. What we're trying to say is because it's namespace, a developer can create it, and any object or any actions that get taken because of the bucket request would also result in namespaced objects or namespaced scope of things. So when COSI sees this bucket request, and if you notice another thing other than namespace, there's also a bucket class. I've shown the bucket class here, and there is no namespace field there. So bucket class is not something that the developer will be able to create. It's something for an admin to do. But I've shown it here. I will expand on it a little later in a few slides from now, but let's keep going here. So a bucket request specifies that it wants a bucket. COSI will receive the request, talk to the backend, object storage backend, and create the bucket in the backend. And once it's created, COSI also creates a Kubernetes bucket. And that's what it looks like. Now, once a bucket is created, it's ready to be used. In order to use it though, you'll have to request credentials for that bucket. Again, declaratively, we model this as bucket access request. It's a declarative API, it's a CRD that expresses the intention to access a bucket. This is what the resource looks like. Again, bucket access request is a namespace resource. It has a bucket access class that it points to, which is not namespaced. The classes are not namespaced. The bucket access request encodes that I want access to a bucket, and COSI sees this object being created. It will go and create credentials and convert the credentials into a format that COSI can later use to put into pods. Basically, it creates Kubernetes secrets from it. Once the bucket has been created successfully and the bucket access has been created successfully, you can now specify this bucket access into your pod, and the pod is also been wired to accept bucket access requests now, and it will go use the new credentials that were created for that bucket, and it will also bring in information about the bucket, the URL, how to access it, and it will put it into a particular directory of your choice into the pod. So pod can just read that directory, look at the files there, and based on that it can start using buckets. It doesn't have to know how the bucket was created, it doesn't have to know how it is wired in, it just opens a file and has a bucket. That's what COSI magic does. Now, so far, if you've been following carefully, you might notice that all of the operations were driven by the developer. There really wasn't any need for an admin so far. I'm pointing it out because this shows that COSI actually enables self-service model of using buckets. So there is no reliance on the developer or on the admin by the developer. So a developer can just use buckets. The admin, I said, still has a role to play, which was setting policies, broad policies, quotas, and access control. The admin can do that using the class objects that I showed earlier. For instance, a bucket class which encodes information about what kind of buckets can be created, what are the properties of such bucket, and what is the driver that's going to make it happen. That is an admin only managed resource, and that looks like what I've shown on the screen. Similar to bucket class, there's also bucket access class, which encodes properties about what kind of access a developer can request for a bucket. So admin controls the classes and developer controls the requests. So as long as the admin has created classes that beforehand, a developer can create as many requests as they would like, to create as many buckets as they would like within the boundaries of what the admin has set with the classes. So this is how we enable self-service. One more thing to notice, which is a little more obvious, is that all the bucket operations that I've shown so far is completely driven using Kubernetes APIs. There was no need at any point in time to short circuit Kubernetes, go talk to the object storage backend directly. Instead, you just talked using the Kubernetes API, just using bucket access requests, bucket requests, and so on. So that was our first use case, which has become kube native and integrate tightly with pods and be namespaced. So out of the three use cases we talked about so far, this API itself enables two of them, kube nativity and self-service. Now we'll look at how it enables portability as well. We discussed that there were two kinds of portability that we wanted to support. One is cross-cluster. Again, I'll go over what cross-cluster means. Cross-cluster means you create a bucket in one cluster, say the blue cluster, and you want to move that bucket to the red cluster. So the way COSI enables this is an admin would have to create a copy of the same bucket object. So when Kubernetes creates the bucket object in the blue cluster, an admin would have to copy that YAML and then push it into the new cluster. Now Kubernetes and COSI would know the configuration of that bucket. Then a developer can create a bucket request that directly points to that bucket. That way there is cross-cluster portability, and that's all it takes. Two resources that need to be created, and just like that you can move buckets across clusters. Second is a different kind of portability, which is cross-platform portability. Cross-platform portability is where you have the configuration in your application to request some sort of bucket, say S3 bucket, which I've shown in green here, specified in the bucket class, and you want to say move away from Amazon Cloud, you want to go on-prem, and say you decide you're going to use MinIO. So because of the way these two resources are defined, where the bucket request is controlled by the developer, the bucket class is controlled by the admin, you can just seamlessly switch the values in the bucket class in your new platform. So the bucket request would have no need for any changes, and it would directly point to the new bucket class, presumably in a new cluster, and it would whenever that is processed by COSI, it'll end up talking to MinIO instead of S3 to provision that bucket. So you'll get buckets from your local on-prem object storage rather than from the cloud. So with no changes from the application's perspective, from the developer's perspective, you can just move across platforms as shown here. So that concludes our API section of the talk. I want to make a pause again here to again recap what we've covered so far. We started with our most important use cases, the reason we built COSI, that is, and they are to provide a kube native API to empower the developer using self-service or by enabling self-service, and also to prevent vendor lock-in using or by enabling portability. And we saw how with bucket requests, bucket access requests, bucket access classes and bucket classes, we were able to achieve our goals stated in our use cases. Now let's go and explore how COSI itself is built internally and how any vendor can become COSI compatible and start providing their object storage service in any Kubernetes cluster. So let's go back to this diagram again. I'm using this diagram again because it acts as a good segue to go from one topic to another. So this diagram again explains the same life cycle that I was explaining earlier, which is it shows the life cycle of a bucket where a pod requests a bucket, and then COSI receives that request, and COSI translates that request into an object storage specific call, and the object storage provisions that bucket, creates credentials for it. COSI takes those credentials, puts it back into the pod, you can use it. So there are two aspects that I mentioned earlier. One is the communication between pod and COSI, which is the COSI API, and two is between COSI and the object storage. We're going to focus on the second part. So COSI itself follows the Kubernetes way of doing things, which is COSI itself is made up of 3 microservices. They are the COSI controller, we sometimes call it central controller, the COSI sidecar, and the COSI driver. So the reason we broke up the controller and sidecar, it was originally a single unit, but then in order to integrate with multiple different vendors, we created the concept of a COSI driver. The COSI driver allows any vendor to work with COSI as long as they support the gRPC protocol spec standard that we've created. And the controller and sidecar originally could technically be one unit, but the reason we broke it is because we wanted to reduce the attack vector between something like the controller, which has broad access to all the buckets in the cluster, and something like the sidecar, which is supposed to be there for every single vendor driver. So there will be multiple COSI sidecars, one for each driver. So you can have multiple COSI drivers in your environment. So you can have multiple object storage systems in one Kubernetes cluster. So the COSI sidecar, the separation is intended to allow the driver and sidecar to work together without disrupting the operations of the central controller and without even having the risk of a bad actor. So let's look at what the COSI controller does and what the sidecar does. So the controller's job is, like I said, to have broad overview of all the buckets in the cluster. It receives every bucket request, it receives every bucket access request, it processes bucket classes, access classes, and so on. And it receives the request and ensures that whatever classes are pointed to are actually valid in two ways. That is, one, the class exists, the configuration is correct, and two is the person or the account that created this bucket request and class actually have permissions to do it. So that is the job of the controller. Once the controller validates everything, it creates an intermediate object that the sidecar then receives, and the sidecar would take that intermediate object, translate that into a gRPC call to the driver. The driver is then responsible for going to the object storage provider either on the cloud or on-prem and taking the necessary steps. So the sidecar, whatever request it receives, it will only respond to requests that are meant for that specific provisioner. So if the provision is S3, then the sidecar for S3 would respond. If the provision is MinIO, then the sidecar for MinIO would respond, but they won't overlap. And the sidecar translates that request, say you're an S3 environment, Amazon environment, and the sidecar would take that request and translate it into a gRPC call to call the Amazon COSI driver, which would then call the necessary AWS APIs to provision buckets and so on. The gRPC API is actually very simple API. Just like I explained early on in this presentation, there are only 3 core primitives that COSI operates on. Similar to that, the gRPC API has only 4 APIs, and it's actually just the amalgamation of those 3 core primitives only. So the 4 APIs that any software, if it supports in this gRPC spec, can call itself a COSI driver. So the first one is bucket creation. Bucket creation is, as the name says, is very simple. It's just creating a bucket. The second one is bucket deletion. Bucket deletion would just go and delete the bucket. Now we have 2 forms of bucket deletion in COSI. One is, and we differentiate between them using something called as deletion policy. So deletion policy, there are 2 deletion policies. One is retain deletion policy, one more is delete deletion policy. In the retain policy, if a bucket is requested to be deleted, then COSI will delete the references to the bucket in the Kubernetes environment, but it will not go and delete the objects, won't delete the data or the bucket itself from the backend. If the deletion policy is delete instead of retain, then COSI would go ahead, talk to the backend, clean up the data, and then clean up the bucket. So you'll also take the data out, reclaim space. The other 2 APIs are for managing access to the buckets. One of them is grant access, one of them is revoke access. Currently we only support token based access, which is access keys and secret keys. Eventually we will also support workload identity based access, which would be something like AWS IAM is one form of workload identity based access. And like I said, any piece of software that supports these 4 gRPC calls according to the spec defined in the COSI gRPC API can call itself a COSI API, COSI driver, sorry. So with that, the presentation actually comes to a conclusion. I hope during the course of this presentation I've answered some of the questions you've had, or I've satisfied your curiosity about COSI. There's a lot more about it, and you can find out all about it on our website, which is container-object-storage-interface.github.io. You can look at our GitHub repository for either the COSI API or the driver API in the repositories shown in this slide right now. It would also be great if you shouted out to me on Twitter or came by our booth, stopped, and we could chat more about COSI. And finally, we also have weekly meetings where we discuss the architecture and progress of COSI. Currently it's an alpha level API, and during the regular course of Kubernetes development it aims to become beta and V1. And you can find out the details about our weekly meetings on that website. Thank you, everyone.